So I'll continue basically from where Amir Yodev left yesterday. So the result I'm going to present fits very nicely into this general theme of generic lower bound proof. So Amir also pointed out yesterday. So basically, in the Amish Pilka and Amir Yodev, they present most of the lower bound proofs in this fashion. So what they say is that a generic lower bound proof has basically this overall structure. So basically there is a so first there is a model of interest. So it's a submodel of arithmetic circuits. So of course this workshop is on arithmetic circuits. So it's a so we don't know how to prove super polynomial lower bound for general arithmetic circuits. So usually people put some restriction. So of course there is a set of restrictions, restriction set on the model, or which defines the model. So this restriction set can be like different things. For example, monotonicity, which you saw yesterday. Then there can be multilinearity, which also you saw yesterday, and so on. And then there is an analog of this restriction depth 4. The model circuits. So when I say some model, of course it means that there is a restriction set here also. So which you can say R4. So this R4 is the corresponding depth 4 analog of R, and the basic lower bound proof, what it does is that it first gives a translation or reduction, from general depth circuits to depth 4 circuits. So which usually you know by the name of okay. So then there are some parameters of this depth reduction. So for example, you can have some restriction on the size, degree. Okay. So corresponding you will get some size, say B of S. So B is the blow up. Circuits in R4 and so on. So let's see some examples to formalize what I'm trying to say. So let's say first example. So these examples are from yesterday only. You have already seen these. So first is monotone circuits. So let's say the size is S, and so let's say you are computing a polynomial of degree D, and then correspondingly so in yesterday's talk Neeraj showed that what you get here is that it can be written in this form. So here the order S. So you have Fi times Gi. So with two restrictions that and the second restriction is that, well, they are not too large. So degree of both Fi comma Gi, let's say 2n by 3, right? So well, it's easy to see that this is a depth. This is a depth 4 circuit. Why? There's a sum gate at the top. So let's say this is sum gate at the top. This is a product gate in the middle. So here is a product gate, and then these two are polynomials. So well, polynomials are computed by again a depth 2 circuit. And then there are variables. So it's a depth 4 circuit, right? Easy to see. So the second example So the lower bound for this model is due to Jerome and Sneer. There are multilinear formulas. So first restriction is multilinear. Also, oh, by the way, so Fi, Gi are also monotone. So this is so then is multilinear formula. So what Amir showed yesterday is that you have a size S multilinear formula. So first restriction is multilinear. Then there is formula, which is another restriction. Then it has size S. So how does it translate? So it is a sum of, so it's called log product representation. So it's 1, 2, plus 1. So you have G1 to G R. So R is large enough, firstly. So these are variable disjoint, firstly. Multilinear variable disjoint. Oh, by the way, by n I will mean the number of variables in everything I will say, unless I mention otherwise. And the variable set of GIs, all GIs is non-trivial. I mean, it's large enough. Linear, etc. So he showed. He proved the lower bound in this particular representation, and it's stated to a lower bound for general multilinear formula. Then there is homogeneous formulas, which maybe this year this will be the model of interest for many people. And I mean, most people would have realized that depth reduction for this particular model is the thing to study, which, I mean, this is the next problem which needs, I mean, people will be studying. So the first restriction is homogeneity. The second restriction is it's a formula. So you have size S, and it's computing a polynomial of degree D. So the corresponding depth for some model that you get, it's by Hrubesch and Yaudayev. So what you get is, it's a similar looking expression. So you have plus 1 into GR. So there is a big correspondence between variable size of variable set here and the degree here. Yeah, and GI is a homogeneous. So this is another way you can reproduce. And well, the next thing to do is that for depth for homogeneous formula, now we have exponential lower bounds. So next thing to do, I mean, what people want to do is they want to prove homogeneous formula lower bound for general depth. And what is the interesting thing to study is to come up with the correct submodel. Maybe this is not the correct model to study in the depth 4. Maybe the correct analog will be the next thing to find, and then you can lift the lower bound to general depth. So, So finally, so what a lower bound proof does is, it proves some lower bound in this particular depth 4 analog and somehow try to lift that lower bound up to the general depth. So finally the whole thing, which is studied by a long series of works by DFDR. So if you think for a moment, then in general, arithmetic circuits can compute polynomials with very large degree. So for instance, you start with a variable x, and so there is a multiplication gate. You feed these two variables here, so it will compute x square, right? This polynomial. Then you compute 2y's again. So this is repeated squaring. And so suppose say the size is n. Then what you will realize is that the polynomial output here has very large degree. So in general, arithmetic circuits, very simple looking arithmetic circuits, can compute polynomials with very large degree. So the next restriction you want to put on your circuit model is degree. Okay, so I put the restriction degree d. So my number of variables is n, and let's say my size is s. So I put these two restrictions first on. So basically, size is just denotation. This is the degree which this is the restriction which I'm putting. So the corresponding, what these people show is that the corresponding depth 4 analog that I get is of this form. So you have let's assume we have to read these. Let's say it's 2. And the blow up on the size that so what is the property of y? So degree of and the blow up that you get is 2 to the okay. Some complexity in fact we don't need to analyze it. So yesterday what we saw was that there is a class of circuits in which if you restrict your circuit class to compute polynomials of degree polynomial in the number of variables of a circuit class, so it's called, so the class is called dt. So under this restriction that d is poly n, s is poly n. This particular class is called dt. So what do you get here? What you get is, and let's say the degree d is n. I mean, so d is n. So what you get is this I is varying, so I mean think of them as indexed by I. I'm not writing it, but there is an implicit I here. Okay. So immediately what you can see is that this gives a way to prove lower bounds for general circuits. So in particular, if you have, so in what particular implication is that if circuits or then by all these people, okay, then what does it imply? It implies that yeah. So one interesting direction to prove that such a thing does not hold is to show S is a okay for the permanent. So this is one direction to show that permanent does not have polynomial size factor. So what this talk is about a result which doesn't really show this, but it shows root n. So which is progressed here. Okay. So this is joint work with British. So Pritish Kamat, who is a student now at MIT, and there is Neeraj, and then there is Ram Prasad. Okay. So the technique to show this lower bound is via something which was defined in the model, right? Something called shifted partial derivatives. Okay, so this particular thing was introduced by Nissan and Wigderson, and then Kayal gave the idea of taking shifts. Okay, so what exactly is the complexity measure? Basically is that we, for a polynomial f, so here's the measure. So it's just dimension of f. So f is a polynomial and you are taking kth order partial derivatives, and then you are just multiplying monomials of degree L. So what is this? This is yeah, right. So what do I mean? What do I exactly mean by this? So it's just some convenient notation. So if m is, let's say, x1 e1 up to x and en, then del so you are just taking partial derivatives respect to as many times as the respect to variables as many times as the corresponding exponents. So, so the proof is basically that. So suppose and so what we do is we just compare the dimension of this particular quantity so right now so there's some so there's one so note that so if we are taking any derivative with respect to anything any we have f plus g then this is a linear operator and so is taking monomial like multiplication with monomial so in particular if you So this operation is linear. That means that if you are taking okay. So what okay. So firstly, what do I mean by dimension? So when you are talking about dimension of a set of polynomials, let's say R, basically what you are doing is that think of these polynomials as it's an element of the polynomial ring and think of the ring as a vector space. So these polynomials will be nothing but vectors. So when you say that you are looking at dimension of a set of polynomials, basically it's the minimum number of polynomials, let's say g1 to g1 to g are such that all fi's are linear combinations of gs. Okay, so this is what you mean by the dimension. So when you say dimension of a set of polynomials, what you are basically trying to say is you are looking at this dimension. So this is a linear operator. So what will happen here is that in particular I can just break. Okay. So imply. What does this imply? This implies the dimension. Right? So in general, this particular quantity is less than equal to plus times. Okay, so what we have is that S is greater than. Right? So basically the proof outline is what you would guess. First, we will try to upper bound this quantity. So here will be the first part. So upper bounding. So we'll be upper bounding the denominator, and the second part would be, so we'll be lower bounding on the numerator. Okay, so let's proceed with the proof. First, we'll see an upper bound on this quantity. So let's see what a polynomial here looks like. So you have, suppose you take a derivative of the polynomial which is inside. Let's say it's d. Okay, right? So note that what is the degree of this polynomial? So all qi's have degree at most root n. So when you take a derivative with respect to one variable, its degree goes down by at least 1, so it's root n minus 1, right? What about here? The degree is less than or equal to again root n minus 1. Now, to take one more derivative, what will it be? It will be, so either you will insert the derivative here, or these two are the only possibilities. Either you will take the derivative in the place where you already took, or you will go pick some new q1. And similar looking expressions. So, so what is the degree here? Let's say I put here. So the degree here is degree of q1 q2 minus 2. So what is degree of q1 q2? Degree of q1 is at most root n. So degree of q1 q2 is at most 2 root n. So when you take derivative twice of this degree, here the degree is less than twice of. What about here? This degree is at most root n minus 1. This degree is at most root n minus 1. So overall degree is 2 root n minus 1. Right? And in every expression you can see that you can write it in this form, and there will be at least d minus 2 qi, some subset of d minus 2 qi's which will be dividing that particular polynomial. So in general, what you can say is that there exist polynomials if you are taking derivative respect to say x1 to xk of t1 td. So this is one particular polynomial. So this combination of so you are summing over all d minus k subsets of d. So there will be times some so there exists some such PIs such that degree of PIs, this degree less than equal to k. So you just continue like this, you will be able to see it. Okay. So in general, one can see is that what one can see. So these PIs will depend upon what is the monomial with respect to which you are taking the derivative, right? But what we can always see is that this definitely belongs to the span of these particular polynomials. So the degree of this polynomial is at most k times root n minus 1. So in general, any such polynomial is a linear combination. Some linear combination, I don't know what, some linear combination of monomials of degree right. So in particular, this particular polynomial also can be written as a linear combination, or belongs to the span of, or in other words is a linear combination of times n, where I1 to Ik range this belongs to span of times n, where I1. So this I1 to ID minus k ranges over all subsets. And this all subsets of D, of size D minus k, and M ranges over degree k times root n minus 1 monomial. Right? Now, when you are so in particular, I didn't use the fact any property of which monomial I took derivative from. This will be true for all derivatives that you take. So in general, what you have shown is that any polynomial in the set of same. Okay, so now the next step what you are doing is you are taking shifts. So what is a shift? You are multiplying all possible. So whatever set you are getting, you are multiplying it with different monomials, all monomials of degree L, and you are getting a lot of polynomials, and then you are looking for a basis. How many of them are linearly independent? So what it also implies is that this where the only difference is that these things do not change. This is okay. Just the degree of the monomials which you are taking changes. Right? So obviously the dimension of the span is bounded by the cardinality of the generating set. So how many polynomials are here? How many ways to choose d minus k size subspace here? So it's definitely less than what it implies. So from there, this will be times how many monomials are there of degree L plus root n minus k times n on n square variables. We are computing the permanent. Yeah, so it's on n square variables. So this is it. Yeah, so it proves that. So let me just write it. Right. Are there any questions? So now the second part is of course lower bounding. This quantity for the permanent, right? So this is what the rest of the talk is about. So you obtain some, okay. So before we move on to what the lower bound is, let's try to just understand what exactly is this set, right? So this particular set, so what is this? This is the set of all n minus k. Yeah. So what do I mean by this notation is basically you are looking at all submit. So what is this? This is that you have so you take a subset of rows here called R, and then you take a subset of columns C, and then you get a submatrix. So I am representing that submatrix by this notation, and then you are taking the permanent of this. This is what the derivative will be. So all such, just go over all possible such submatrices and square submatrices of size n minus k. Take the permanent, and you'll be able to see that this is the case. Why? So let's see a simple example. So note that permanent is multilinear. So let's take one specific example. Let's say right. So when you will be taking the so by the way, the permanent is yeah, right. So when you will take the derivative respect to, let's say for example, symmetric, all of them are equal. So let's say you take the derivative respect to x11. So this doesn't depend on x11 anywhere. So you will get you will only get this, right? And without loss of generality, when you are taking the derivative respect to this, you will get permanent of this, and then it's the same structure. It's a permanent of a submatrix, and go on. So you can easily see that it is indeed this is the case, right? So then okay, so now that we have started to look at variable matrices, let me also define something called monomial. We'll also be requiring this. So what is this? So admissible monomial ordering. What do I mean? We want to define a total order on all monomial. just say that. So we should be able to compare two monomials, two distinct monomials, either. So if we have m1 not equal to m2, we should be able to say that either m1 is strictly greater than m2 or right. So the ordering that we would be interested in will be Lex ordering, and the corresponding variable ordering will be this. This will be, so you have so the ordering is that the first row always, so it starts from the first variable, decreases here, then decreases, then comes to second row, then decreases this way, and then so on. Okay. So variables in smaller rows are always bigger than variables in larger rows. I mean, bigger as in like in terms of higher order. So so what is the property of Lex ordering? Lex ordering says is that x11 is higher ordered than any monomial not containing x11. So in general, I would be only concerned with multilinear polynomials. That is why I am just giving this particular thing. So okay. So here's the definition. So suppose you have a polynomial f, then the highest rated, so the highest, I mean in terms of this ordering, the highest ordered monomial of f is called the leading monomial. Denoted by L, right? So I'm running out of time for video this afternoon, because then you should have learned after this. So here's the fact that the dimension of a set of polynomials R is at least the number of distinct leading monomials okay. So why is this? Let's say without loss of generality, leading monomial of f1 is strictly less than leading monomial of fk. Rest of them I don't know. So So when you will represent this polynomial as a vector, these polynomials as a vector, what you will observe is that f1, fk. So leading monomial f1 is the smallest. So what does that mean? That this will be. So leading monomial of f1 is the smallest. That means these all monomials do not appear in f1. So these are 0. So this is non-zero. 0 or no, I mean, right? Let's say 1. Okay. Then you look at f2. So note that here after f2 it doesn't appear because I'm assuming this is also 1 and these do not appear and so on. So what you will see is that you will have a lower triangle. It's easy to see that this is polar. Correct? Is that okay? So what now? So if you see, just think for a minute, the monomial ordering that we have defined forces. So if you have so leading monomial of permanent of this matrix is exactly the principal diagonal. Why? Because in all the monomials which in only so x11 is the leading. So x11, any monomial containing x11 is bigger than every. So consider monomials which contain x11, so it will be reduced to permanent here, and then just go on. You will have x2 and so on. You have this is the leading monomial, right? So now what you are doing is that you have so the leading monomial here. So note that when you so leading monomial here is just the diagonal corresponding to r comma c. I'll just denote that. So now when you will be multiplying a monomial. So let's say if you multiply a monomial or take the shift, your leading monomial will not change. It will be just that monomial times, right? So in general, the set of leading monomials of this set is exactly right. So dimension of this is at least by this particular fact is at least the cardinality of leading monomial. Set of monomial, which is nothing but all monomials. So degree L plus n minus k monomials containing right? So all we need to do to lower bound this quantity is that we have to lower bound the cardinality, or we just have to count monomials. So we have reduced a problem of lower bounding a rank of a matrix to just counting monomials. Okay? So how to count these monomials? So in general, we can lower bound that quantity by this particular. So just look at the middle two diagonals. So look at the middle diagonal and the diagonal above it. So that quantity is at least number of L plus n minus k L plus n minus k monomial containing n minus k length diagonal from these middle two diagonals, at least n minus k length diagonal from, let's say V1, V2, I'll call the middle diagonal as V1 and call the above diagonal as V2. Okay. So in general, moreover, you can bound this quantity itself by, you run over all subsets of the middle two diagonals. Right, so you run over all subsets, okay, and you make sure that the support of the monomial which you are considering just projected on the middle two diagonals, restricted on the middle two diagonals, is exactly that. So what I'm saying is that first you put so the monomial that you consider, first just put all the variables in S. So it contains a n minus k length diagonal, so your property is satisfied. This property is satisfied. Now all you want to ensure is its degree is large enough. So what is the degree freedom that you have? The original monomial should have degree L plus n minus k. So now you have degree L minus k minus S, right? But you don't want to double count. If you will pick variables from after picking a subset from middle two diagonals, you might end up having some intersection or overlap or overcounting. So you want to avoid that. So you just pick this particular support, put it here, and allow only variables from the rest of the matrix. So this particular part, and you can also allow S itself. So it will make sure that at least when your support of the monomial projected on the middle two diagonals is exactly S. So you'll never double count. So the size of the variables allowed here is of course n square minus 1. These are the number of variables in the rest of the matrix, and you are also allowing S. So plus. So how many such things are there? Right? So now what you do is that, okay, so now what you do is you just club this according to size. So this is just club it. I'll define what this quantity is. Okay, so where this quantity denotes number of subsets of D1, D2, D2 of size exactly n, containing a diagonal containing n minus k length. Okay, right, this is exactly the same. So now what you need to do, you just need to lower bound this one. This is easy enough to lower bound. It will just require 5 minutes. Okay, so how do we lower down this particular quantity? So let me just prepare the plane. So first I will show that this quantity equals the number of r diagonals or length r diagonals in B1 union B. Okay. So in general you have x and 1. Now if you pick in your diagonal this particular variable, then you cannot pick this because a diagonal is a permutation. So all you need to ensure is that if you have picked this, then you cannot pick this and this, but rest of them are okay. So that means that you can pick this also. So anything basically. So a diagonal, if you think about it, a diagonal is nothing but, so it's a subset. What is a diagonal? It's a subset. So let me just order these. So I'll just order this way. It's y1, y2 up to y2 and minus 1. So what is a diagonal? Just subset of y1 to y2 and minus 1 r such that no two elements are adjacent, right? So firstly, what is this number? So this number is basically, so just let your first choice, let's be after a1 distance from 0. So it's after a1 distance. Then the second element is after a2 distance from the first choice, and then so on. R, right? You are picking R element, right? So what is the condition? A1 does not have any condition. So A1 has to be just greater than equal to 0. What you need to ensure is that the second and the third element are not conjugated. So A2 has to be greater than equal to 1 and all of the rest. Correct? And moreover, you have picked these, let's say, as your elements. And this distance or the distance between them are the rest of the variables. How many rest of the variables are left? So you had 2n minus 1 variables to begin with. You picked R, so rest of them are 2n minus 1 minus 1. So what you need to ensure is that this is summation of 2. The rest of the distance or distance is the number of variables which you are not picking in between the two which you have picked. Correct? So what is this quantity? The number of solutions of this. Essentially, well, one way to look at this is just counting monomials. You have R variables, and you want to ensure, and you want to pick all of them have support at least one. So you just pick. So you have, usually you would do this, and if there was no condition, then you have 2n minus 1 minus r. But now you have to ensure that the support is, at least each of them has support. So just you have put it there, and you have small, your freedom in choosing large duty is there. So minus r, minus This is right. So minus r. So AI, no, so AI is the distance between the variables which you have picked. So that distance means the number of variables which you have not picked. So for example, if I pick y2 and y4, then the distance is number of variables which will not be picking, right? So which is 1. Two and minus 1 has to be the rest of the rest. Well, 10 plus minus 1 plus. Yeah, that's what I mean. Okay, plus minus 1 will do. Let's see. So but there will be a minus r. Okay, so this is it. So so r here is n minus k, of course. So r is written, r is n minus k. We have to put r to be n minus k. So this we have to. Now I want to note that this point. So this is 2n minus r. Some plus minus 1. Forget about the plus minus 1. Okay. And now I want to claim that actually the number of subsets, what is n? Then in this case we have y1, y2 minus 1, which we have already arranged of size exactly m in containing r diagonal. So what you do is you pick this is what you do. So you have this diagonal. So suppose this was your diagonal. So this, the crosses denote the diagonal. So let's say it's d1, d2 up to dr. So note that these two are not adjacent, so there will be at least one element just on the right of d1. Call it the right neighbor of d2. Then there is d2. Let this be the right neighbor of d2, and so on. So how many neighbors are there? There are exactly r right neighbor. And pick any. So in your subset, let this subset be. You pick this particular diagonal. So you have picked this set of diagonal d1, yeah. So you had to choose a subset of size m. So r you have already picked. The m minus r, you pick anything from anywhere in the right neighbor of this diagonal. So how many of them are there? R. So how many subsets can be there? R to m minus r. Okay. And the claim is that they will all be distinct. Firstly, for a fixed diagonal, you are choosing different subsets. So anyway, they will be distinct. But note that in the monomial ordering which we have defined, if any monomial I add, I look at the highest order r diagonal possible. Then this is the highest ordered r diagonal possible in this subset. So if I choose, let's say, this subset, union of this subset, then note that this variable is higher than everything. So I will first pick this, but now I cannot pick the adjacent one because I have to pick a diagonal. So I will remove this. Then I will go here, I will pick this and so on. That means in the process, my highest order diagonal does not change. So for different diagonals, my highest order diagonal are distinct. So these subsets will also be distinct. That means that particular quantity, this is the number of diagonals, which is 2n minus r plus minus 1. root r times the choices of just the right neighbor which I am adding to this. So that is it. So the final lower bound that we have here is for this quantity, is at least so you are able to see it. Okay, so you just need this plane and in this particular expression. Okay. So you have this quantity evaluated and you have also upper bounded this quantity. So you just take the ratio of these two. So finally your S will be this quantity by this quantity that we just write down here. So now you want to maximize this for appropriate over the choices of L, K and M. So I will not show how, I will not show the calculation, I will just write down the parameters. So your L, for which this is maximized, will come out to be n square root n. Your K will be epsilon root n and your M will be n minus 1 alpha. They will exist epsilon and alpha. So the lower bound that we get is S. Okay? Yeah. Okay, so I have overshot the by 10 minutes. So might as well make 4 more minutes. So I'll just take 4 more minutes. So I just wanted to show an upper bound on what is the limit of the technique, which I think will be a good idea to show. So in the proof there will be a lot of inequalities, and a very reasonable question to ask is that, this is one lower bound, but this is not tight, and most probably it is not tight for permanent. I'm sure the actual quantity is much more bigger. It's conjectured to be significantly bigger than this. But the question is, what is the best you can do? So the best you can do is that, so assuming the upper bound is this, so you have so the best you can do is how many polynomials are there in this set, like the number of just a trivial upper bound. So I will show you 2 trivial upper bounds. Every polynomial here. So firstly, how many polynomials are you trying to bound the dimension? The number of operations here, how many of them are there? N square plus L. Okay. Also, permanent is a degree n polynomial. You are taking derivatives of order k, so you get polynomials of degree n minus k. Then you are adding monomials or multiplying monomials of degree l. So final polynomials, every single polynomial has degree l plus n minus k, right? So a trivial upper bound on the dimension is just the number of monomials of this degree on n square variables. So this always is less than minimum of like you cannot do better than this unless you improve this particular upper bound. You cannot get a better lower bound, right? Now, so what is the maximum value of this quantity? So note that so this and this. So for a non-trivial lower bound, you need your n minus k definitely has to be larger than this. So I mean L will be the significant term here. So what we have is which implies that k has to be less than root n, right? Now, but if k is less than root n, then note that this quantity is anyways less than this quantity. So I mean the only thing, this is always less than, so only thing you can get a lower bound from is this quantity, right? But if k is root n, then the best you can do is this, and this is, you know, is 2 to the root n. So 2 to the order root n log n, and for crossing the chasm, or for your lower bound to lift up to give super polynomial circuit lower bound, you need later omega here. Right? So for separating VP and VNP, this technique, well, we always know that this technique, I mean this particular measure cannot separate VP and VNP, but what we believe is homogeneous formula should be possible. So if you are interested in proving super polynomial circuit lower bounds, it will be good to explore mean complexity measure. If you are interested in proving lower bounds which are not as strong as arithmetic circuits, then it will still be this.